Hello, in this video we're going to be talking about net force analysis, how to use free body diagrams along with F equals ma to solve any and all forcey and acceleration-y kinds of problems. Here we go. Alright, first thing, as basic as it might seem, is you need to have a clear idea of what a force is. And here's about as good a definition as we can do. A force is tough to define because it's so fundamental. The one part I would like you to really focus on is this. It's a push or pull, but it's exerted on one object by another object. It is always one thing pushing or pulling on another thing, and you need to be able to define those two objects. If you can't state which object is pushing or pulling on which other object, you don't really fully understand what force you're talking about. You really need to, every time you talk about a force, think about what object is pushing or pulling on what other objects. Be able to name and draw the two objects. That is very important and often overlooked. All right, force is a vector quantity. It, of course, has a magnitude and a direction. We use the Newton for the unit of force whenever we're doing all our calculations. If it helps, the unit you might be more familiar with is a pound. And a pound, well, let's say it this way. A Newton is about a quarter of a pound. So you can imagine like a delicious cheeseburger or something, right? A Newton is a derived unit. It's not a fundamental unit. You want to have the 7 fundamental units memorized. So we need to break a Newton down into its fundamental units. This is the most common one by far that you have to memorize as a derived unit, what it's made up of. So Newton is a kilogram meter per second squared. Good way to remember this is think F equals ma. Since a Newton is a unit of force, it has to be equal to the units of m times a. Right, mass is kilograms, acceleration is meters per second squared. So we're going to draw free body diagrams to represent all of the forces acting on one object, only one object. So we're not dealing with any third law action-reaction pairs because that involves forces on two objects. We're just looking at one object, drawing all of the forces acting on that one object from any number of other objects. Of course, we show the direction of the force with a vector. We show the magnitude with the length. So a long arrow to the right represents a big force to the right. Short arrow down, small force down. You don't have to get too meticulous with this. It just needs to be by eye about right. All right, if you have two equal balanced forces, they should look the same by eye. You should, honestly, with a ruler, more or less use the measurements on the ruler to draw them the same length. But to be honest, nobody's going to measure your forces with the ruler and make sure that they're exactly the same, as long as they pretty much look like they're obviously meant to be the same length. And if one force is obviously bigger than the other, it should be drawn to be obviously larger. You can see these two ways. The IB tends to like you to draw them from the point of contact. Sometimes, though, you'll see them where all the forces are just drawn from the center of mass to simplify things. But it is good to try and draw your forces like where they're acting. So if we're talking about, say, friction, we're going to draw it on the ground to represent, on the bottom of the object to represent that the friction acts between the ground and the object. The originating point of the line should be at the point of contact. So the tail of the vector goes at the point of contact. And we'll look at some of those. All right, some common forces you will draw on your free body diagrams. Of course, the weight of an object you'll draw many times. Every object has a weight because every object has mass. And we're assuming, for the most part, that we're dealing with objects near the surface of Earth. Obviously, if other things are going on, then maybe this will be slightly different. But pretty much every time you ever draw a free body diagram, you're going to draw the force of gravity as a vector pointing straight down because it points towards the center of the Earth, because, of course, this is the force between the Earth and the object we care about. All right, weight and force due to gravity all mean the same thing. We calculate this near the surface of Earth, at least we can calculate this with a simplified equation of just mg, right? Mass times acceleration due to gravity. If you label a force vector as little g, that's not gonna cut it. right? That's an acceleration. That's acceleration due to gravity. That's not the same thing as the weight. Please make sure you are good and clear on the difference between the weight of an object and the acceleration due to gravity. You'll use one to calculate the other. And even that we will have to amend once we start dealing with like stuff in space and stuff not near the surface of Earth. All right, but force due to gravity, weight, they mean the same thing. They are the force acting on the object from the pull of the Earth, calculated in a simplified way by mg. The normal force is another force that comes up a lot. The IB uses R for the normal force. R stands for reaction. And it's honestly a good way to think of the normal force, which will help you out in remembering that it's not always equal to gravity. All right, the normal force really doesn't have anything to do with the force of gravity. In a lot of problems, it ends up being equal to it, but that's only because there's nothing else going on. All right, it's called a reaction force because it's literally a surface's reaction to a force being applied to it, and it's the surface's reaction so that it doesn't break. So if you push down on your desk is going to push back so that it doesn't break. Right? If you push down more, the desk will push back more. If you push less, the desk will push back less. So if you're just standing on the ground, then yeah, the ground is pushing up on you with a force equal to your weight to keep you from breaking through the ground. But that's just a situational thing. All right, so the only rule is that it's the force from a surface. It acts perpendicular to the surface. That's what normal means. In math sense, normal means perpendicular. All right, but just be careful. Don't ever assume that the normal force is equal to the weight of the object. You need a free body diagram to justify that. More and more as we get into IB physics, you will see that that's not always the case. You're going to see plenty of problems where that's not true. So you need to do an FBD and a net force analysis to find the normal force. There is no formula for the normal force. A lot of times you'll draw an applied force on your free body diagram, and this is just sort of a catch-all term we use. If you're like pushing on a block, we just say it's an applied force. All right, so if there's a better name like tension or something like that, you want to use those as well. But an applied force comes up enough that we'll call it a common force. It's just a general name for a push or a pull that doesn't have a specific name. We will also see many resistive forces in our problems. A resistive force is a force that will oppose the motion of an object. So whenever you see a resistive force, that tells me about the direction. So the direction is always exactly opposite the direction of the velocity of the object. Because it tries to slow it down, and velocity is which way you're moving, right? So if it's moving to the right, a resistive force would push to the left. If it's moving down, a resistive force would push up. If it's moving up and to the right at an angle of 30 degrees, the resistive force will be down and to the left, exactly 180 degrees away from the velocity. So there's a couple types that we will see. Oops. Friction is one. We'll talk more about this in a future lecture. But friction is a sliding force between two objects in contact. The IB will call this solid friction. It's two surfaces. So we'll either slow down or prevent sliding. Air resistance, which we talked a little bit about in one of the motion videos, is another resistive force. It's not the same thing as friction. You can think of it as a type of friction, but their air resistance and this type of friction are different things. So air resistance, we also call it drag, we also call it fluid resistance, results from moving through a fluid. Air is a fluid. Gases and liquids are considered fluids. So air counts. When you move through the air, you have to push the air molecules out of your way. That costs energy, and so that slows you down. If you remember, we talked about this one increases with speed, so it's got all kinds of fun stuff going on. You'll see a couple different ways that this is labeled. You can do whatever you like as long as it's clear. F sub D for the drag force, F sub air for air resistance, capital D alone sometimes just to mean drag. Any of that is all good. And keep in mind, most of the time, it's okay to ignore these. You want to read the problem and decide based on the problem whether friction and air resistance need to be included. You'll basically be told assume friction if like a block is sliding on the ground, but you wouldn't assume air resistance. Air resistance is almost always negligible unless you're going really fast. All right, and if you're just like pushing and pulling stuff around, blocks and stuff like that, the air resistance is so small, it's like 0.0000001 newtons. It's so small, it won't have any impact on your answer. So it's not even something we're doing just to like ignore what's really going on and make the math easy. It literally has no mathematical impact on your answer. Most of the time, it's so small. But just read the problem, make sure you're clear on whether you should include friction and or drag. All right, so here's a very simple free body diagram just to kind of look at the different pieces of it. So we can see this is a very classic, you pull a thing to the right, it drags on the ground, nothing is going on vertically, and we draw the forces acting on it. So we have an applied force pulling it to the right, a force of friction to the left. Notice the force of friction is acting between the surface and the block. We can see that clearly here. We can also see the applied forces acting on the right side. Notice you want to draw the point of contact where the end of the arrow is. So this shows me that this is pulling it to the right. Same thing down here, that we draw the normal force starting from the bottom and pointing up because the normal force is from the surface upwards. And the force of gravity we always draw from the center of the mass. The force of gravity truly does act from an object's center of mass. So there you go. We can also see the weight and the normal force in this case are equal because there's nothing else happening vertically. There's no angles. And we can see the applied force is much bigger than the force of friction. So we imagine this thing is probably going to accelerate to the right. All right, then we get into net force. Net force is a mathematical thing. So if I take all of the forces acting in one direction, in one dimension, either X or Y, that's the net force. And it turns out net force is proportional to acceleration, which gives us the classic equation, net force equals ma. This really should be broken into two separate equations. The net force in X is equal to mass times the horizontal acceleration, and my vertical net force is equal to mass times vertical acceleration. You have to break this into two separate equations. Just F equals ma is not detailed enough. You might end up dealing with too many forces, acceleration in different directions. You have to really take your time and break it down in your mind in this way. So all of the forces added together horizontally are equal to the mass times the acceleration in that direction. All right, m is the mass of the thing being accelerated, so it's the mass of the object in the FBD. It would be the mass of the block here. And keep in mind, net force is not its own separate force. It's a mathematical thing. So you never ever draw it on an FBD, right? When we're looking at this free body diagram, we don't have an arrow for net force because it's not a thing that's actually pushing or pulling on the block. The net force is just what I get when I add the applied force to the force of friction. The vertical net force is the value I get when I add the normal force to the force of gravity, which is 0. Right, so the net force is a math thing. You don't draw it on the FBD. You use it to analyze an FBD. And you do that like so. So here's the steps you should take. This is a general thing. You don't have to like memorize a set of steps or anything, but these are just some guidelines. And sometimes you might flip this around depending on what you're looking for. But you always want to start, if you're doing an F equals ma problem, you need a FBD. You absolutely should have a free body diagram. You should make it cleanly and nicely, use a straight edge, use a ruler, measure the lines, make sure that they show the lengths relatively. Then probably start with the X dimension, but obviously depending on the problem, you might choose to start with the Y dimension. You might not need X at all. But we'll say starting with the X dimension, you sum the forces. You add all of the forces together. Any forces to the right are considered positive. Any forces to the left are considered negative. Then you sum those forces and you set that sum equal to ma. For the X dimension, we'll set it equal to mass times the X acceleration. Do all your algebra before you plug in any numbers, so solve for what you need to, then substitute it and get your answer. And then you do the same thing for the Y dimension, but you have to do all this stuff for X and then do all this stuff for Y. or maybe vice versa, or maybe you just need one, but make sure that you're only ever dealing in one dimension. So here's a very, very, very basic example of that same problem, that same FBD from before, but now we're going to do some numbers. So we'll say I apply a force of 85 newtons and the friction force is 15 newtons. All right, this is like trivially simple, but just to show how the math works, and especially so we're clear on what the net force thing means. So net force in X means the sum of all the forces horizontally. So I'm going to take I have two horizontal forces, the applied force and the force of friction. Those two forces get summed, meaning if the applied force is positive, the force of friction is negative. I always write out plus FA minus FF. Like I always put a plus in front of the forces that are positive just to make sure I am consciously going through and assigning a direction to every force. Obviously, you don't need that math-wise, but it's helpful to include. And this is the net force. That's the sum of the horizontal forces, and I set that equal to MAX. Now it's cake. I just solve for A, plug in my numbers, I get 7 meters per second squared. So there's my acceleration. All right, so that's a very basic example, but just to show you mechanically how this works, what we mean by the net force. But you can apply that to any of the crazy, crazy, crazy problems that'll be coming your way. All right, so use this as a guideline and have fun.